You know that feeling, right? You pull off a sweater in a dark room and see those little sparks fly, or you reach for a car door and zap, you get that little shock. Well, those tiny moments are actually driven by one of the most powerful and fundamental forces in the entire universe. And in this explainer, we're going to pull back the curtain on the science that connects that little zap to a massive bolt of lightning.
So let's kick things off with a little mystery that you've probably already experienced. What on earth could a huge thunderstorm, a fuzzy sweater, and your car door possibly have in common? I mean, they seem totally unrelated, but it turns out they're all linked by the exact same physical principle.
And that connection, of course, is static electricity. It's a phrase we all throw around, especially when the air is dry, but what is it really? Well, we are about to unpack this whole shocking feeling right down to its core.
The answer, the culprit behind it all, is electric charge. See, all these things happen when these tiny invisible charges build up on a surface, like your clothes or the metal on a car, and then, all at once, they leap off. That sudden discharge releases energy. And that's the spark, the shock. It's basically a miniature lightning storm happening right at your fingertips.
So, that begs the question, what is this charge and what are its rules? Well, the investigation started thousands of years ago, not in some fancy lab, but with a simple piece of amber and a bit of wool.
It's pretty wild when you think about how long it took us to figure this all out. It literally started back in ancient Greece, with someone just noticing that if you rubbed a piece of amber, it could magically pick up little bits of straw. Fast forward a couple thousand years, and experimenters started realizing, hey, there isn't just one type of this, there are two. And then finally, along came Benjamin Franklin, who gave them the names we all know today, positive and negative.
So these early scientists, they started noticing a very clear pattern. If you took two glass rods and rubbed them both with silk, they'd get the same kind of charge. And when you brought them close together, they'd actually push each other apart. Same exact thing happened if you used two plastic rods rubbed with fur. They repelled. But here, and this is the key discovery, is where it gets really interesting. What happens when you bring the charged glass rod near the charged plastic rod? They have different kinds of charge, and they didn't push away. Nope, they pulled right towards each other.
And all of this boils down to a beautifully simple set of rules that govern every single electrical interaction in the universe. Just by convention, we call the charge on the glass rod positive and the charge on the plastic rod negative. And from that, we get the two fundamental laws. Like charges repel each other, and opposite charges attract. Simple as that.
Okay, so knowing that they attract or repel is one thing. That's cool. But in science, that's not enough, right? The real question is always, how much? How strongly are they pushing or pulling? That's the next big piece of this puzzle.
So, in the 1780s, a physicist named Charles Coulomb measured this force with incredible precision. And he found two main things. First, the more charge you have, the more force you get. Makes sense. But the second part is the real game changer. The force weakens like crazy with distance. If you double the distance between two charges, the force between them doesn't just get cut in half, it drops to 1/4 of what it was. It gets weaker, fast.
And when you start to really dig into the numbers behind this force, you uncover something absolutely mind-blowing. We're all familiar with gravity, right? It keeps us on the ground, keeps planets in orbit, but on the scale of atoms, gravity is, well, it's a lightweight. It's incredibly weak compared to the electric force.
I mean, just look at this number. It's almost impossible to even wrap your head around it. This is how much stronger the electric force is compared to gravity for a single proton and electron. We're talking about a force that's 10 to the power of 39 times stronger. It's not just a bit stronger, it's on a completely different level of reality. It's astronomically more powerful.
Okay, that incredible strength brings up a huge kind of spooky question. If you've got two charges just sitting there in totally empty space, how does one know the other one is there? How can it push or pull on something without touching it? There's nothing connecting them.
So, how does this action at a distance actually work? It was a puzzle that completely stumped early scientists. The answer was a totally radical idea, a real game changer. What if the space between them isn't really empty after all?
And this is where the amazing concept of the electric field comes in. The idea is that a charge doesn't directly feel another charge. Instead, it alters the very fabric of space around itself, creating this invisible field of influence. Then, when another charge comes along, it's the field right at that spot that gives it a push or a pull. It's an absolutely brilliant way to explain how forces can act across a total vacuum.
Now, to help us see this invisible field, we draw these things called field lines. Imagine you could drop a teeny tiny positive charge near a bigger one. The path it would get pushed along, that's a field line. So for two positive charges, you can see the lines radiate outwards and curve away from each other. It's a perfect picture of repulsion in action.
Now check this out. When you have opposite charges, the story is completely different. The field lines flow directly from the positive charge and curve right into the negative one. You can almost see them, like invisible elastic bands, just pulling the two charges together. This is a visual map of what attraction actually is.
And these amazing invisible force maps have a few simple unbreakable rules. They always start on positive charges and end on negative ones. They can never cross, because if they did, the force at that point would be going in two directions at once, which is impossible. And here's a cool one. Wherever the lines are packed tightly together, the field is super strong. Where they spread out, the field is weaker.
So here's the really big takeaway. This force isn't just about static shocks and lightning. The electrical attraction between a positive nucleus and negative electrons is literally what holds atoms together. The forces between those atoms that create molecules, that build everything you can see and touch, solids, liquids, gases. It's all fundamentally electrical. This force is the silent architect of our entire world.
And that leaves us with one final fascinating puzzle to think about. If this electric force is trillions upon trillions of times stronger than gravity, why don't we feel it constantly? Why does gravity, the ridiculously weaker force, seem to run the show in our everyday lives? It's a fantastic question, and the answer is pretty surprising.